breaking the wall of the dark side of the oceans. How marine sciences discover hidden resources. Peter Herzig, Geomar, Helmholtz Center for Ocean Research.
On the 9th of November 1989, when the wall came down in my home country, Germany, I was away in Canada doing geological research on a postdoctoral grant by the Alexander von Humboldt Foundation. I thought to myself then, the world changes whenever you really don't expect it.
Good afternoon, ladies and gentlemen. It's a pleasure to be here. And it's even more of a pleasure to talk about breaking the wall of the dark side of the oceans. Because breaking the wall of the dark side of the oceans actually means breaking the walls of one of the last frontiers on planet Earth. And one of the last frontiers on planet Earth is the deep sea. What I would like to do this afternoon is to share with you three of the most extraordinary discoveries that we have made in the deep ocean over the past 10 years. And in order to do this, I would like to take you on a journey to the deep ocean floor. So what we will do now is we will all go on board of the French research submersible Nautil. Nautil has a diving capability of 6,000 meters. We will be diving on a spot that is located about 500 nautical miles south of the Tonga Islands in the Southwest Pacific, in the middle of nowhere. And we will be looking at the ocean floor in about 3,500 meters depth. So here is Nautil. Nautil has a crew of three, a pilot, a co-pilot, and a scientist. Here we are being deployed from the support vessel Nadir into the dark blue waters of the Pacific Ocean. As you will see in a minute, the diver will be disconnecting the submersible from the support vessel. There is a pre-diving check as in an aircraft. And in a minute, we will be descending to the seafloor. It takes us approximately 2 hours to arrive at 3,500 meters depth. And we have to turn the lights on because after 200 meters, the sunlight is off. And 2 hours later, here we arrive at the seafloor. We see unique biological communities living here in the dark, in the cold, in a hostile environment. We see white smokers where hot seawater is being pumped out of chimney-like features. And we see big blocks that look like rocks, but those blocks are not rocks, they are ore samples. The rocks here contain high concentrations of copper sulfides, of lead sulfides, of zinc sulfides, of silver and gold. And this material is produced by the activity of white smokers, of gray smokers, as we will see in a minute, and also of black smokers. There are extinct chimneys that have a height of approximately 35 meters. And in a minute, we will be looking at a larger field of white smokers. Here the smoke mainly consists of finely dispersed silica with a high concentration of dispersed sulfide minerals. And here you see the central complex, a central black smoker complex. The temperature of the fluid here is 350 degrees centigrade. And those black smokers pump out several hundred tons of ore every day that are then deposited at the seafloor. Diving with submersibles is a lot of fun. I've done it several times. I have to admit that these days we have turned to remotely operated vehicles that we are using to do the job for us. This is a system that is capable of diving to 6,000 meters water depth. It is equipped with two electro-hydraulic arms that allow us to do experiments at the seafloor, to take samples, to do surface installations. It has a number of thrusters and can fly above the seafloor and do certain operations. This is a very similar system that has a diving range of 3,000 meters. And here I show you the winch that is important to run those systems, because the submersibles are maneuvering freely, but the ROVs, the remotely operated vehicles, they are attached to the support vessel by a cable. A cable means a steel cable that has a copper line in the center for energy transfer, and that has a fiber optic line in the center for the transfer of information. So here are the pilots. They are not sitting in the sub at the seafloor, they are sitting on board the support vessel quite comfortably. Two pilots, the chief pilot and the co-pilot, and they run the system from the vessel. And here I have another video to show you how such a system is being deployed from, in this case, the German research vessel Sonne in the central Atlantic. We go here to 6,000 meters depth. The operation is being done from the support vessel, as I said, and here you can see in a minute that we have actually reached 5,987 meters. That is much faster than we can do it with a submersible. This is what it looks like down there. It is volcanic rocks. It is a very strange environment, strange life down here, an octopus at 6,000 meters depth. And of course, this is what we are looking for, black smokers. Those black smokers here have temperatures above 400 degrees centigrades. The fluid does not boil because of the water pressure. And here you can see that the pilots on board the vessel 6 kilometers higher up are trying to take a temperature measurement. They try to place a temperature probe into the orifice of the chimney, the black smoker chimney, and as I said, the temperature here is in excess of 400 degrees centigrades. And the black color of the smoke is an indication of a high concentration of copper sulfides, of zinc sulfides, of lead sulfides, of gold and silver within this smoke, which is actually not smoke, it is hot seawater. This is what we are looking for. On the right you see a sample from the Galapagos Spreading Center that we have collected a number of years ago with a TV-guided grab system. The sample has a weight of approximately 1.5 tons, and it is highly concentrated base metal ore with high concentrations of gold. And on the left side you see a sample that we have collected from the territorial waters of Papua New Guinea. This sample has a gold concentration of 250 grams per ton. These days we are mining land deposits for 2 grams per ton, so we are talking different dimensions here. However, in order to estimate the metal content of such a resource down at the seafloor, we need to do drilling, and this is what the mining industry is planning to do. And those samples, of course, have triggered the interest of the mining industry, and the big challenge is now to find ways to mine those ores in a sustainable and environmentally friendly way. Another discovery that I would like to share with you is this, that we have black smoker chimneys and hydrothermal areas where we have oases of life, where we have a very large biological community. There are shrimps that we have discovered here that don't have eyes. They have temperature sensors in order to make sure that they don't get into the 400 degrees centigrade water. They like to live more comfortably in 30 to 40 degrees hot water, and the active hydrothermal sites that we have looked at in the world oceans are approximately 250, so we have many places where we have hydrothermal activity. Another discovery that I would like to share with you is this one. We have made that by accident from a US Navy vessel close to the island of Guam. This is a submarine volcano erupting in front of us. In front of us means in front of the ROV. We are up on the surface vessel. And this is something that has never been seen in this way before. When you watch very carefully, you can actually see the flames coming out of the volcano. and you can hear the noise. So this is a very dynamic environment. And this is how Iceland was formed a long time ago, or how the Canary Islands were formed many million years ago. We have been in this area because we were looking for hydrothermal sites, and by accident, as I said, we have found this eruption that takes place here at 556 meters of depth, and is something that is extremely unusual to see. Another interesting discovery that we have made over the years is that of the discovery of so-called gas hydrates, methane hydrates at the seafloor. We have used a manned submersible that we operate that is having a diving capability of only 400 meters, but the material that we are interested in occurs in approximately that particular depth range. This is the submersible Jago that has a pilot and one scientist instead of two pilots in the big subs with one scientist. So here we go to the seafloor close to Iceland, and we have taken some samples from the area, and what we have got here is called gas hydrates. This is solid material consisting of water and natural gas in solid form. We also talk about burning ice because this material forms at the seafloor at about 400 meters of water depth, 40 bars, and the ambient temperature of approximately 2 degrees centigrade. I have another video here that we have taken offshore Oregon. Here we have sampled gas hydrates from a larger field with a TV-guided grab system, as you can see here. This is the material, what it looks like when it comes up to the surface. And as you will see in a minute, when you put it at fire, it starts to burn, because 1 cubic centimeter of this material contains 164 cubic centimeters of natural gas. So here we are talking about highly concentrated natural gas in so-called gas hydrates. This is not a scientific curiosity. We have done a lot of research on this, and we have found out that the energy in gas hydrate deposits around the world is about twice as much as the energy that we still have in conventional oil and gas deposits on land. So the big question is, do we want to touch this large reservoir of fossil energy, or do we want to leave it where it is? Natural gas could be supplied from gas hydrates for a long, long time. Natural gas is clean energy, as you know, only 50% of the CO2 output relative to coal. There is a lot of gas out there. This is actually all I wanted to say at this point. It's time to come back to the surface. I'd like to remind you that 70% of the planet are covered with seawater. 60% of this is deep sea. We have probably looked at 5 to 10% of this. So there are many more walls to break in the future. Thank you very much.